Thanks for the intro, and thanks to the organizers for bringing us all together this week. Okay, this talk starts with a little cartoon picture of the scientific method. As you'll see, I'm a theorist. Okay, and this is what I learned in high school, basically. So if we're doing an experiment, the idea is that we'll make a hypothesis. We'll, based on the hypothesis, make a prediction, and experimentally verify the prediction. So it's kind of a linear process. And of course, we're aware that there's a difference between the theory and the practice. But the main goal is to have this hypothesis, predict, and verification paradigm. With the advent of quantum computers and the possibility that we'll eventually be able to run large-scale quantum computations, this raises a question, namely, how are we going to apply the scientific method to experiments that perform quantum computations? The problem here, of course, is that the predictions of quantum mechanics are thought to be exponentially difficult to compute. So it seems to be impossible, at least in a reasonable amount of time, to make a prediction based on the postulates of quantum mechanics. So hence, we can't predict ahead of time what the quantum computer is expected to do. So therefore, how can we verify that it's correct? It really looks like we're at a crossroads here, and we need an alternative to the standard predict and verify paradigm to verification or to the experimental process for quantum computing. So this is an example. We're not going to talk any further about boson sampling, but just to show you that we're already reaching the limits of what we can predict computationally, but however we can build some of these experiments. So boson sampling is a problem of sampling. So this experimental setup samples from the binomial distribution. Put a marble here, and then it goes down here, and that gives you a probability distribution. This one here samples from the boson sampling distribution, and it's reputed to be difficult to simulate classically. And already we have small-scale boson sampling experiments, and we're already asking the question, how does one know that the outcome of the boson sampling experiment is correct? Of course, here we're talking about at the scale where classical simulations are not possible. And there's already, this question has been looked at in the literature. I'm not sure if there's a consensus or a final answer, but this is definitely an area of current questioning. The problem we want to look at today is more general than boson sampling. We want to look at general quantum computations. So we'll take the viewpoint of the experimenter being a verifier, and they are classical, and they run in polynomial time. And the experiment, we'll also call that the prover, and it's quantum, and it runs in polynomial time. So everything should be efficient. We should be able to do this experiment in a reasonable amount of time, and as well as the verifier, where the verifier would be a classical device. Okay, so we'll picture that the verifier has a circuit. It's a public circuit. Everybody knows what it is, and the verifier wants to know the output of that circuit, and wants to use the prover to help him compute that. Another way of seeing this is that the prover wants to become convinced that the output is correctly computed, and the prover would like to help with that. So a little bit more specific, if you look at the circuit, something like this, we're interested in the final output bit. It's a classical bit that's measured. And a yes instance is a circuit where the probability that the bit is 0 is larger than 2/3. And a no instance is a circuit where that probability is smaller than 1/3. And you've heard me talk about completeness and soundness yesterday. This is a little bit more technical. If a circuit is a yes instance, then there should exist a prover such that the verifier accepts with probability at least 2/3. And soundness, if this is a no instance, no prover, even unbounded, can cause the verifier to accept with a probability greater than a third. And these numbers, 2/3, 1/3, are kind of arbitrary. What's important is that there's a completeness soundness gap that's inverse polynomial. Okay, so if you're wondering how can we possibly verify a quantum computation, some solutions that you may come up with are to test small parts and to assume that they work correctly when you put them together. Right? So maybe you test little parts, and those are reasonable. You can simulate them efficiently, and then you assume that when you put the whole computer together, that the behavior remains the same. Well, this is an extra assumption, namely that the behavior remains the same when you put the pieces together. So we don't want to make that assumption. Another thing you might think of is to test computations that are easy to verify. And this is reasonable, especially there's a lot of problems for which the quantum computer has this property, for instance, factoring. If you're given a claimed solution to the factoring problem, it's easy to put the numbers together, multiply them, and check that it's a solution. But this does not cover what are the hardest quantum problems. The hardest quantum problems are called BQP complete, including things like approximating the Jones polynomial. So for these problems, we don't know of an efficient way to verify the solution. And another BQP complete problem that we're going to use today is to evaluate this circuit, as I mentioned in the previous slide. So just to predict the outcome bit here of a circuit, this is one of the hardest problems for quantum computers, for generic circuits. So from this slide, I can kind of also motivate why this talk is appropriate for QCrypt, because this is really a cryptographic problem. We're dealing with a quantum computer, and we're treating it as an adversary. We don't trust it at all. We want to be sure that it produces the correct answer from the point of view of it being completely malicious. Okay, so proofs. Proofs are things that are convincing. You can verify a proof, right? Static proofs have one round, let's say. For instance, the verifier can ask a large composite number to the prover, and the prover can return two numbers that are claimed to be the prime factors of the number, and then the verifier can check. And this is probably the first notion that you would think of in terms of a proof and a verification process. And indeed, there's an entire complexity class based on this. NP is the class of languages that admit such types of proof. We call it MA if the verification is probabilistic. Hence, by the way, the QMA I was talking about yesterday, quantum MA. So, in order to answer our question about verifying quantum computers, let's go to classical complexity theory and look at what's been done there before. So the question being, can we verify more than MA? So can we verify more than in this static scenario? And the answer is a resounding yes. We can increase the power of the verification process by adding interaction. And Where's Waldo is a tough act to follow, but at least I have a story in this presentation. So the story illustrates the power of interaction. And it's a story of a mother and her child, and they're sitting under a tree. And the child says, "Mom, I can count the number of leaves on this tree." And she says, "Wow, that's amazing. Prove it to me." So the child looks up and is counting, and then he says, "There are 300,856 leaves on this tree." Okay. So what's the mother going to do? She doesn't have the power to count the leaves on the tree. Any ideas? How can she verify? Yes, okay. So she will blindfold the child, put the child in a safe space, and climb up the tree, remove a constant number of leaves, let's say 6, destroy the evidence, and then say, okay, child, turn around. How many leaves are on the tree now? So he looks, 300,850. And if I remember correctly, the difference is indeed 6. So in this case, there was a challenge, and the prover, the child, has managed to succeed at this challenge. So they can repeat this, and suppose the child keeps on getting the right number. This increases the verifier, the mother's confidence of the power of counting the leaves, or kind of the number of leaves, not exactly. The analogy breaks down somewhat. But you can see that she does not need the power to count the leaves in order to verify someone else's claimed power. Okay. So interaction increases the power of the verification process. Formally, this is known as IP equals P space. Everything that can be computed in polynomial space, which is a lot of things, can be proven in an interactive process. So this is much, much more than NP that we talked about previously. This result is in a slightly different model. We have a polynomial time verifier and an unbounded prover. Okay, so let's use this idea for verifying quantum computations. Let's allow ourselves interaction. Okay, so again, our picture, prover's polynomial time, verifier. Oh yes, the verifier is going to be almost classical. It's going to have a little bit of quantum power, and I'll tell you what exactly later. So, as an experimenter, I'll suppose that I can verify and characterize very simple quantum systems. I can predict the output of trivial quantum computations, for instance, evaluating the identity circuit on input 0. And I can interact with the setup. And the main result in this presentation is that if we use 1, 2, and 3, we can bootstrap these 3 assumptions into the verification of a general quantum process. So basically, small quantum capability coming from the first step here, plus 2 and 3, implies full verification. And I'd like to emphasize that this problem has been looked at before, and there's been solutions proposed before. In interactive proofs for quantum computations, there was a method that was proposed that used techniques from cryptography, namely quantum authentication codes. And so the verifier would encode the data into quantum authentication code, send it to the prover, and then they would use interaction as well as auxiliary qubits that were encoded in order to do this verification process. The main inspiration for this technique was prior work for quantum multiparty computation. The drawback is that the proof of this one depends on the proof of this one, and the proof of this one is only really just a sketch. So we didn't have a full proof. The other drawback is the requirements from the point of view of the verifier required an encoding technique as well as a method to perform computations on the encoded data. There's another approach that originates from blind quantum computation. And the idea from unconditionally verifiable blind quantum computation is to encode a computation into a graph state. And within that graph state, some of the qubits are in a deterministic state. So these ones, they have measurement results that are known ahead of time. And if the prover does not return the correct measurement result, then we can conclude that there's been a problem and we can reject. These are called trap qubits. And the disadvantage here is that for a single quantum computation, we need to encode it into a much larger computation because we need to take into account these positions that need to be added. So that's also one of the drawbacks of that scheme. So one of the starting points of this work was to say, okay, well, what's the important ingredient in these protocols that make them work? And can we possibly come up with a simple protocol? And can we also have a convincing proof of soundness? So what's the secret to make these protocols work? Well, they all had some sort of cryptographic aspect in terms of hiding the input or the computation or both. And this leads to a way to test the prover, because the prover can't tell if it's doing some part that's actually the computation or some part that's actually test. So that seems like a very important ingredient. And another one is that they both had some sort of computation by teleportation. It's very obvious in the measurement-based approach, and it's also present in the authentication code approach. And this gives a way to somehow verify the intermediate steps. We'll have a more concrete example soon. And then the question is how to prove soundness. It's always very tricky. And what I came up with was a new technique. Well, no, the technique is old. It's been known for quite a while to use reduction to an entanglement-based protocol. But I use this for the first time in the context of verification of quantum computations. So I'll go into more details shortly. So the moral of the story is that we don't need any encodings. All we'll need is a form of encryption plus some sort of random choice from the point of view of the verifier. Okay, so for this slide, I think I can go quickly. We're going to use the following universal gate set in order to represent the quantum computation that we want to do. And to be a bit more specific on the main theorem, we said that the verifier would need a little bit of quantum power. Well, the verifier needs this following box. There's a setting, and when the verifier presses the button, the prover will get one uniformly random state in the set Si, where I is the index that the verifier chose, and the verifier gets the classical description of that state. This is kind of like a BBD4 box, right? It would kind of generate these states. The state would go straight to the prover, and then the verifier would know which state was generated. So if they share this box, V is classical polynomial time, P is quantum polynomial time, then we can prove there's an interactive proof for all of BQP. And to be more specific on these sets, we have S1 being 0, 1, S2 plus minus, S3 P plus and P minus, and S4 has 4 qubits possible, T plus, T minus, PT plus, and PT minus. Okay, so the very high-level idea in this protocol is that there's going to be test runs, and there's going to be the computation run. And the verifier is going to choose randomly which type of run to execute at any given point in time. And the prover will not be able to tell what type of run is currently being executed. So these are indistinguishable from the point of view of the prover. And then we'll look at the behavior of the prover, because of course we have to have soundness against any possible prover. And we'll conclude that there are two cases. Either the prover is benign. So benign means it's not really doing anything bad. And indeed, if the prover is benign, the output of the computation will be deemed correct, and the verifier is going to use that to decide whether to accept or reject. And then there's non-benign provers, and these will all be detected in the test run. So these test runs will be coordinated to detect any type of non-benign prover. Okay, a little bit more details is that in the computation run, we'll evaluate the actual circuit on input 0, which is, of course, the computation that we want to perform. In an X-test run, we will compute the identity on input 0, and there's going to be internal checks also. And a Z-test run is going to compute the identity on input plus, and also internal checks. So we said that the verifier should not be, the prover should not be able to tell what type of run is being executed, and this is going to be achieved using cryptographic techniques. Namely, we're going to encrypt all the communications to the prover, and the prover will need to perform computations on encrypted data. Very importantly, the instructions to the prover are identical, whether we're doing a computation run or a test run, and only the verifier will know how to decrypt and interpret the results. Okay, so encryption. The basic encryption we're going to use is the quantum one-time pad. You may have heard of the classical one-time pad. And the quantum one-time pad is an analog for a single qubit pure state. We need to encrypt it with 2 classical bits. And it essentially boils down to applying a random poly. And we call this the key. AB is the key. And without knowledge of the plain text, the ciphertext always appears as a maximally mixed state. Okay, so next we need to do computing on encrypted data. So at the high level, it looks like this. You take an input row in, and you encrypt it with random keys. These are the red things, A1, B1, A2, B2, A3, B3. And then you send the encrypted data to the prover. The prover's in this box. And then there's a specific circuit that should be implemented. And for each circuit element, there's a specific subprotocol, a gadget, if you want. Coming into these circuit gadgets, we have specific keys on each wire. And each gadget is going to have its own key update rule. So it'll tell the verifier how to update the keys in a way that if we were to decrypt at each point if we were to decrypt each wire, we would get the state corresponding to applying the computation on the plain text, so without any encryption. Okay, so we have different gadgets for the different gates. For the 2-qubit gates, we update 2 wires, of course, etc. So Clifford group gates are really easy to do on this encrypted data. Of course, it's the property of the Clifford group to be the normalizer of the poly group. Namely, for an X gate, we just do the X, and the keys stay the same. Same thing for Z. Control not slightly more complex, but it's essentially this linear key update. Remember that we have test runs, and they are performing the identity on input 0. So it's convenient here for us that if you do control not on 2 wires that are 0, or 2 wires that are plus, they remain unchanged. Of course, the non-Clifford group gate, here in this case the T gate, also called the pyrite gate, is going to be an issue. It doesn't have a nice property of just having to update the poly key. In particular, it picks up this P to the A that is outside of the realm of poly encryption. So how are we going to do this? We're going to use auxiliary qubits and interaction in order to perform the T gate on encrypted quantum data. Okay, so the way to read this is that we have an input qubit here that the prover has. The verifier prepares an auxiliary state here. Y, E, and D are random bits. And then the prover does a control not between the data wire and the auxiliary wire. A measurement, reports the measurement result C, and then the verifier sends a classical bit A XOR C XOR Y. And note that Y here is part of this auxiliary qubit, C is this bit here, and A is the key. So very important that this process would not leak any information about that key, because otherwise you wouldn't have the indistinguishability that we're counting on. And this is the key update, slightly complicated, but it works. So the result is that we've applied the T gate on the plain text up to some poly correction. And the X test run has to be applying the identity on input 0, but however, the prover should be seeing exactly the same thing. So from his point of view, everything is identical here, because he doesn't know the keys. And, but from the point of view of the verifier, we've maintained this invariant that the wires are all 0. And this also gadget has a verification. So this outcome is deterministic. We expect it to be A XOR D. A is here and D is here. And if it's not, we reject, because we know that we've found some deviation. Okay, and the Z-test run is similar. It doesn't have a verification. It consists of generating these auxiliaries, sending a classical bit, and the point is that it does the identity up to some polys. Okay. And remember my claim about these 4 sets. Here's where we need these auxiliary qubits. We're going to need the computational basis states here, the P plus and P minus states down there, and the 4 possibilities arise here. Actually, there's 8 here, but we can simplify that and by some relabeling. This X doesn't really have to be there, and we only need 4 possibilities. Okay, the Hadamard gate, it's a Clifford gate, but so you could just do it on the encrypted data, but it doesn't maintain this nice property of, if you did a Hadamard on the first wire, it would become plus. If everything was 0, did a Hadamard on the first wire, it would become plus, and then the bottom wire would be 0, and then if you did a C0 in the future, it would entangle these wires, and you would not have this nice, simple to compute computation in the test runs. So the solution is to use this identity. HPHPHPH is equal to H, and HHHH is identity. So in the test runs, we can replace the P with identity by using some of the gadgets that we had in the previous slides, whereas in the computation run, we'll actually do the P. So we'll be doing HPHPHPH, which will implement the Hadamard. And we use P is T squared. So this is nice. And it also explains why we have an X test run and a Z test run. Because as we're going along and doing this on a single wire, we will momentarily swap the role of the X and the Z test, because the Hadamard is going to swap zeros and pluses. And therefore, the Z tests are also sometimes used to detect errors. That is, namely, within the H-gate gadget. Okay. In order to analyze soundness, as I mentioned, the technique was to reduce to an entanglement-based protocol. So this technique is attributed to Shor and Preskill in 2000, who gave one of the first complete proofs and simple proofs for the security of BB84. And the trick here is to see encrypted qubits as half EPR pairs, which they are, right? So you can get this basically also from the teleportation identity. If you look at teleportation, before you do teleportation, the qubit on the other side is encrypted. The classical bits that are sent in the protocol can be replaced by random bits. And this is how we can do this. This is the protocol that I've already presented, and this is the entanglement-based protocol. So this dash box prepares a EPR pair, and when we do this, we effectively can delay these choices of what are the gates that we apply here before we do the measurement. And that allows us to first choose a random classical bit to send to the prover, and then based on that random classical bit, later on, we can do these gates. Right? Namely, here this Y is A XOR C XOR X. So it's determined later after the measurement result C is returned. So this is about changing the order of the operations in the protocol in order to actually make it non-interactive and to make it easier to analyze. Okay, yeah, so as I said, the verifier delays the choice of which type of run to execute. Importantly, the prover must behave identically in the test or in the computation runs, because from his point of view, they're both the same. So the soundness is the same in both protocols, so let's analyze the soundness of this entanglement-based protocol instead. And, okay, so imagine that we're working with the classical one-time pad, and that you're an adversary, you have access to this ciphertext. So you don't know the key, you don't know the plain text, but you can tamper on the communication channel. Then the effective action of the adversary will be to introduce bit flips. We kind of see that intuitively. Whatever action you could do could be instead pictured in terms of probabilistically flipping bits of the plain text. This is a quantum analog to this observation, and it's called the polytwirl. It's one of my favorite, it's a simple trick, one of my favorite tricks. So if we encrypt a quantum state, attack it with a unitary U, and then decrypt it, so right, we have P, and U will be in this, given in this poly basis, so a P, sum overall P Qs, Q primes, P, Q, P star. Then by the polytwirl, actually we can represent this as the simple application of a poly on the plain text, if we take into account the encryption and decryption. So that's the polytwirl. So basically the quantum one-time pad is going to break up any adversarial attack into a convex combination of poly attacks. And then it's easier for us to analyze only poly attacks. Okay, so the next step is to simplify an arbitrary proof strategy. So we delay all measurements. Suppose that V is going to perform the measurements at the very end. And write the proof strategy as the honest strategy, C, followed by a cheating map. And decompose that cheating map in its Krauss terms. And this is what the system would look like before the measurement, where psi is depending on what we're actually doing in the protocol, if we're doing a test, a computation, etc. So we have the encrypted state, the honest thing, the attack. And then let's quantumly decrypt with P tilde star, which is computed by the key update rules that we've seen. And this gives us a polytwirl on the attack, which is really great. Because when we write the attack in the poly basis, we can simplify everything to be this simple expression. So all we need to do now is to analyze the poly attacks. And namely, yeah, okay. For the computation run, it's slightly more complex because we don't have this simple form. We can't just write a single equation for what the input is and what the computation is doing. So what we can do, this is an equivalent circuit that does the same computation, but we can write x to the d here, attack, and then measurement, and then some reinterpretation of the measurement result in terms of C XOR D. So there's this computational basis measurement, and on either side there is a X poly. So that also gives you a twirl on the qubits that are measured in these auxiliary states. So that's also very handy. And then what are the effects of the possible poly attacks here? Well, if you have an X or a Y attack here on the measured qubit, it's going to flip the measurement result C, and then this P correction is going to be applied when it should not, or vice versa. So the computation will be corrupted, it's going to be wrong. So these are the types of attacks that we need to detect. These are the non-benign ones. The benign attacks, this is also still non-benign. These are attacks on the output qubit. They will also flip the outcome bit, and these ones are also bad. There's also the benign attacks. So there's no X or Y poly on the measured qubits. Both test runs are going to accept. And the computation run, well, by assumption, if you do the honest computation, you have a probability at most 1/3 of accepting. So this bounds our acceptance to 7/9. And in the case of the benign attack, non-benign attack, then one of the test runs is going to reject. So that's because in the X test run, we have this gadget that has a deterministic measurement outcome, and so either one of the X test or Z test runs are going to reject, and that's going to leave our acceptance at most 2/3, which is the probability that we've picked that, that we have not picked the run that's going to detect that attack. Okay, so also an important note is that this proof assumes quantum mechanics. So this is about testing, not about testing quantum mechanics itself, but about assuming quantum mechanics and then testing that our device behaves accordingly, without having to make the prediction ahead of time, of course. Okay, so as conclusion, we remember that, take-home message, if you remember only one thing, is that the interaction increases the power of the verification process. And I'm looking forward to seeing how this is going to affect the way that we can conceptualize experiments in the future. Our protocol is relatively simple. We've managed to get rid of any type of encoding that's required. And if we want to increase the soundness, all we need to do is to repeat the protocol. So it's my understanding that it's easier to repeat an experiment with different initial conditions than to make a larger one. And also, this EPR proof technique seems to be really relevant in terms of proving soundness, and also in the context of verification. An open question would be to have a fully classical verifier. So our verifier here needed some small quantum power, namely the box that was able to generate these random qubits. No quantum memory and no quantum computation per se, but we needed to trust that small device. So open question would be, could we possibly reduce that and have a fully classical verifier in order to verify all of BQP? Thanks a lot.
All right, we have a minute or two for questions. Could you use this proof to have a two-prover classical verifier protocol?
No, I don't really see how this, well, okay, I thought about it. So can we use this proof to have a two-prover classical verifier protocol? And possibly by adding an extra layer of verification of what states they're actually holding. So because we have this box, it really helps us to say, okay, this is the quantum part, and this is how we can mathematically represent it. But it gets a lot more difficult when you have the two provers and you don't really have that. Of course, we know that Reichart and Guru-Vazirani have a solution in that model, but I would not be surprised if this gives a different approach that would give a similar result.
Other questions?
Another question, could you approach to kind of password verification? Could you use the same approach to kind of password verification and problems?
Can we use the same approach for?
Password.
Password. Like password authentication? I don't know. If we can frame it in terms of a BQP problem, then yes. But it might be a more special case type of solution that would be more appropriate than this generic thing. Yeah.
All right. Let's thank Anne again.